So welcome, everybody. My name is Yuanji Li. I'm an assistant professor of physics in the physics department. And I will be your instructor of this semester on AO3. So of course, one first question you have is, why do we want to learn about vibrations and waves? Why do we learn about this? Why do we even care, right? The answer is really, really simple. If you look at this slide, you can see that the reason you can follow this class is because I'm producing sound wave by oscillating the air. And you can receive those sound waves. And you can see me. That's already amazing by itself because there are a lot of photons or electromagnetic waves that are bouncing around in this room, and your eye actually receive those electromagnetic waves. And that translated to your brain waves. You will start to think about what this instructor is trying to tell you. And of course, all those things we learn from AO3 is closely connected to probability density waves, which you will learn from AO4, quantum physics. And finally, it's also closely related to a recent discovery of the gravitational waves. When we are sitting here, maybe there are already some space-time distortion already passing through our body, and you don't feel it, okay? When I'm moving around like this, I'm creating also the gravitational waves, but it's so small as to be detected, okay? So that's actually really cool. So the take-home message is that we cannot even recognize the universe without using waves and the vibrations. So that's actually why we care about this subject. And that's actually why this subject is so cool, even without quantum, without any fancy names, okay? So what is actually the relation of AO3 to other class or other field of studies? It's closely related to classical mechanics, which I will use it immediately. And I hope you still remember what you have learned from AO1 and AO2. Electromagnetic force is actually closely related also. And we are going to use the technique we learned from this class to understand optics, quantum mechanics, and also there are many, many practical applications which you will learn from this class. This is the concrete goal. We care about the future of our space-time. We would like to predict what is going to happen when we set up an experiment. We would like to design experiments which can improve our understanding of the nature. But without using the most powerful tool, it's very, very difficult to make progress. So the most powerful tool we have is mathematics. Okay, you will see that it really works in this class. But the first thing which we have to learn is how to translate physical situations into mathematics so that we can actually employ this really wonderful tool to help us to solve problems. Once we have learned that, we will start to look at single harmonic oscillator. Then we try to couple all those oscillators together to see how they interact with each other. Finally, we go to infinite number of oscillators. Sounds scary, but it's actually not that scary after all. And we will see waves, because waves are actually coming from infinite number of oscillating particles, if you think about it. Okay? Then we will do Fourier decomposition of waves to see what we can learn about it. We learn how to put together physical systems. That brings us to the issue of boundary conditions. And we will also enjoy what we have learned by looking at the phenomena related to electromagnetic waves and practical application in optics. Okay? Any questions? If you have any questions, please stop me any time, okay? So if you don't stop me, and I'm going to continue and talking, okay? Okay, so let's get started. So the first example, the concrete example I'm going to talk about is a spring block, massive block system, okay? So this is actually what I have on that table. So basically, I have a highly idealized spring. This is ideal spring with spring constant K and the natural length L0. Okay, so that is actually what I have. And at t equal to 0, okay, at t equal to 0, what I'm going to do is I'm going to actually move this mass a little bit, and I hold this mass still and release that really carefully. Okay, so that is actually the experiment which I'm going to do. And we were wondering what is going to happen afterward. Will the mass actually move? Will it stay there? Will it just disappear? I don't know before I solve this question. Okay? Now I have put together a concrete question to you, but I don't know how to proceed because, okay, you say everything in words, what I'm going to do, I mean, I don't know, right? So, as I mentioned before, there's a really powerful tool, mathematics, right? So I'm going to use that, okay? Even though I don't know why mathematics can work. Have you thought about it? Okay, so let's try it and see how we can make progress. So the first thing which you can do, okay, in order to make progress is to define a coordinate system. Okay, so here I define a coordinate system which is in the horizontal direction, is the x direction, and the x equal to 0, the origin, is the place which the spring is not stretched, is at its natural length. That's actually what I defined as x equal to 0. And once I define this, I can now express what is actually the initial position of the mass by this coordinate system. x0, it can be expressed as x initial. And also, initially, I said that this mass is not moving. Therefore, the velocity at 0 is 0. Okay? So now I can also formulate my question really concretely with mathematics. Basically, you can see that at time equal to t, I was wondering where is this mass. So actually, the question is, what is actually x as a function of t? Okay? So you can see that once I have the mathematics to help me, everything becomes pretty simple. So once I have those defined, I would like to predict what is going to happen at time equal to t. Therefore, I would like to make use physical laws, right, to actually help me to solve this problem. So apparently, what we are going to use is Newton's law. And I'm going to go through this example really slowly so that everybody is on the same page. So the first thing which I usually do is now I would like to do a force diagram analysis. Okay? So I have this mass. This setup is on the Earth. And the question is, how many forces are acting on this mass? Can anybody answer my question? Yeah.
So acceleration and the spring force.
Okay, so your answer is 2. Any different? 3. Okay, very good. So we have 2 and 3, and the answer is actually 3. Okay, so look at this thing, run in and the product here. So this is actually the most difficult part of the question actually. So once you pass this step, everything is straightforward. It's just mathematics. Okay, it's not my problem anymore, but the math department, they have problem. Okay. All right. So now let's look at this mass. Okay, there are 3 forces. The first one, as you mentioned correctly, is F spring, okay? It's pulling the mass. And since we are working on Earth, okay, we have not yet moved the whole class to Moon or somewhere else, but there will be gravitational force pointing downward, okay? But this thing is actually putting, the whole setup is on a table, a frictionless table. Therefore, there will be no more force, right? So don't forget this one. There will be no more force. So the answer is that we have 3 forces, okay? The normal force is actually a complicated subject, which you need to understand that with quantum physics, actually, okay? Okay, so now I have the 3 forces, and now I can actually calculate the total force. The total force F is equal to Fs plus Fn plus Fg. Okay? So since we know that the mass, okay, is moving in the horizontal direction, the mass didn't really suddenly jump and disappear, right? So it's there. Therefore, we know that the normal force is actually equal to minus Fg, which is actually Ng in the y direction. And here I define y is actually pointing up, and the x is pointing to the right-hand side. Okay? Therefore, what is going to happen is that the total force is actually just Fs. Okay? And this is equal to minus k, which is the spring constant, and x, which is the position of the little mass at time equal to t. Okay? So once we have those, forces and the total force, actually we can use Newton's law. So F is equal to m times a, and this is actually equal to n d squared xt dt squared in the x direction, and that is actually equal to n x double dot t x. So here is my notation. I'm going to use each of the dot is actually differentiation with respect to t. Okay? So this is actually equal to minus kx t in the x direction. So you can see that here is actually what you already know about Newton's law, and that is actually coming from the force analysis. Okay? So in this example, it's simple enough such that you can write it down immediately. But in the later examples, things will get very complicated, and things will be slightly more difficult. Therefore, you will really need the help from the force diagram. Okay? So now we have everything in the x direction. Therefore, I can drop the x hat. Therefore, finally, my equational motion is x double dot t. And this is equal to minus k over n x of t. Okay? To make my life easier, okay, I'm going to define omega equal to square root of k over n. Okay? You will see why afterward. Okay? It looks really weird why Professor Lee wants to do this, but afterward you will see that omega really have a meaning. And that is equal to minus omega squared x. Okay? So we have solved this problem, actually, right, as a physicist. Okay? Now the problem is, what is actually the solution to this second-order differential equation? And as I mentioned, this is actually not the content of 803, actually. It's the content of 1803, maybe. Okay, how many of you actually have taken 1803? Oh, everybody knows the solution. So very good, I'm safe. Okay. So what is the solution? The solution is x of t equal to a cosine omega t plus b sine omega t. So my friends from the math department tell me secretly that this is actually the solution, okay? And I trust him, okay? Him or her, okay? So that's very nice. Now I have the solution, and how do I know this is the only solution? How do I know? Actually, there are two unknowns, right? Just to remind you about what you have learned. There are two unknowns, and if you plug this thing into this equation, you satisfy that equation, okay? If you don't trust me, you can do it after, offline. It's always good to check, okay? So to make sure that I didn't make a mistake. But that's very good news. So that means we will have two unknowns, and also it satisfies the equation. So by uniqueness theorem, this is actually the one and the only one solution in my universe, also yours, which satisfies the equation. Okay, so because of the uniqueness theorem. Okay, so I hope I have convinced you that we have solved this equation. So now I take my physicist hat back, and now it is actually my job again. So now we have the solution, and we need to determine what is actually these two unknown coefficients. So what I'm going to use is to use the two initial conditions. Okay, the first initial condition is s of 0 equal to x initial. The second one is that since I release this mass really carefully, and the initial velocity is 0, therefore I have x dot 0 equal to 0. Okay, from this you can plug these two conditions into this equation. You can actually figure out that A is equal to x initial. Okay, and the B is equal to 0. Any questions so far? Okay. Very good. So now we have the solution. So finally, what is actually the solution? The solution we get is x of t equal to x initial cosine omega t. Okay, so this is actually the amplitude of the oscillation, and this is actually the angular velocity. Okay, so you may be asking why angular, where is the angular coming from, right? Because this is actually a one-dimensional motion, and where is the angular velocity coming from? And I will explain that in the later lecture, later part of the lecture. Okay, and also this is actually a harmonic oscillation. So what we are actually predicting is that this mass is going to do this, okay? Have a fixed amplitude, and it's actually going to go back and forth with the angular frequency of omega. Okay, so we can now do an experiment to verify if this is actually really the case. Okay, so there's a small difference. There's another spring here, but essentially the solution will be very similar. You may get this in the P set or exam, right? Okay, so now I can turn on the air so that I make this surface friction this, and you can see that now I actually move this thing slightly away from the equilibrium position, and I release that carefully. So you can see that really it's actually going back and forth harmonically. Okay? I can change the amplitude and see what will happen. Whoa, the amplitude is becoming bigger, and you can see that the oscillation amplitude is really depends on where you put that initially with respect to the equilibrium position. I can actually make a small amplitude oscillation also. Now you can see that now the amplitude is small, but still oscillating back and forth. Okay. So that's very encouraging. Let's take another example, which I actually rotate the whole thing by 90 degrees. Okay? You are going to get a question about this system in your PSAT. The amazing thing is that the solution is the same. Oh, what is that? And if you don't believe me, let me do the experiment. Okay, I actually shift the position. Okay, I change the position, and I release that really carefully. You see that this mass is oscillating up and down. The amplitude did not change. The frequency did not change as a function of time. It really matched with the solution we found here. It's truly amazing, no? The problem is that we are so used to this already. You have seen this maybe 100 times before my lecture. So therefore, you got so used to this. Therefore, when I say, OK, I make a prediction, this will happen, you are just so used to this, so you don't feel the excitement. But for me, after I teach this class so many times, I still find this thing really amazing. Why is that? This means that actually mathematics really works. First of all, that means we can use the same tool for the understanding of gravitational waves, for the prediction of the Higgs boson, for the calculation of the property of the quark-gluon plasma in the early universe, and also at the same time, the motion of this spring mass system. We actually use always the same tool, the mathematics, to understand this system. And nobody will understand why. If you understand why, please tell me. I would like to know. I will be very proud of you. René Descartes said once, but in my opinion, all things in nature occur mathematically. Apparently, he's right. Albert Einstein also once said, the most incomprehensible thing about the universe is that it is comprehensible. So I would say this is really something really we need to appreciate and really need to think about why this is the case. Any questions? Okay. So you may say, oh, come on, we just solved the problem of ideal spring, right? Who cares, right? It's so simple, so easy, and you are making really a big thing out of this, right? But actually, what we have been solving is really, really much more than that. This equation is actually much more than just a spring mass system, okay? Actually, if you think about this question carefully, there's really no Hooke's law forever, right? Hooke's law will give you a potential proportional to x squared. And if you are so far away, you pull the spring so really hard, it can store the energy of the whole universe. Does that make sense? No, right? At some point, it should break down, right? So there's really no Hooke's law. But there's also a Hooke's law everywhere, right? If you look at this system, it follows the harmonic oscillation. If you look at this system, I perturb this, it goes back and forth, right? It's almost like everywhere. Why is this the case? I'm going to answer this question immediately. So let's take a look at an example. So if I consider a potential, this is an artificial potential, which you can find in George's book. Okay, so V is equal to E times L over X plus X over L. And then if you plot this as a function of X, then basically you get this funny shape. Okay, it's not like proportional to X squared. Therefore, you will see that, okay, the resulting motion of the particle, if I put a particle in this potential, it's not going to be harmonic motion, okay? But if I zoom in, and zoom in, and basically you will see that if I am patient enough, I zoom in enough, you see that, this is a parabola again. You will follow Hooke's law, okay?